The next trend in our list is ionization energy. Ionization energy is one of my favorite ones, and it's also one of the most frequently asked about on standardized tests if you ever see one. The definition of ionization energy is the energy required to remove an electron from an atom. And then it does go on to say in the gaseous state. We normally just kind of ignore that part of it. It measures how strongly attracted the valence electrons are to the nucleus of an atom. There's a little formula for it. If you will, let me write it here on the screen. If we had element X is going to lose an electron, which is going to leave behind a positive ion of element X. And this process is endothermic. That's why I put a positive sign for this enthalpy term here. It is endothermic. It requires us adding energy to an atom to make the electron go away. Take a look at the periodic table on the screen, and the numbers in the boxes are the energy values associated with those atoms' ionizations. Just take a look at it, see if you can find a trend. Well, the trend is fairly obvious. As you go down a column, in every column, the ionization energy decreases. That is the opposite of what we saw for the atomic radius and the ionic radius. And that's a very good, helpful thing to remember. It's the opposite of radius. Ionization energy decreases as you go down. And I'll talk about why here in a moment. But then as you go across a row from left to right, there is an increase in the ionization energy. It becomes harder to take electrons away as you go towards the noble gases. And I think that probably makes intuitive sense for you. But then again, we'll talk about why in a second. The lowest ionization energy elements, and this is important for you to know, are the alkali metals on the far left. The easiest one to remove an electron from is cesium. Again, we're skipping francium because it's radioactive. There's not much of it. But it only takes about 375.7, I believe these units are calories here. That's the energy required to turn cesium into a cesium ion and free up an electron. Much easier to do than even barium with 2 valence. But did you see any blips in the trends? Did you see anywhere going from top to bottom or from left to right? Any places where the trend didn't hold? Most of you, at some point, given enough time, would have noticed some problems right in this area. Nitrogen actually has a higher ionization energy than oxygen does. That seems like a blip. The reason lies in the orbital notations for nitrogen and oxygen. On the screen, I've drawn the orbital notation for the valence shell, the p electrons for nitrogen. There are 3 p electrons, 1 each in the x, y, and z orbital. And if we go to oxygen, the next electron would come as a down arrow in any one of these 3 orbitals. Well, how does that make it easier? Shouldn't it be harder? Well, no, because putting this electron in a pair, in an orbital that already has 1 electron in it, is going to cause that electron to have more energy already from repulsion with its neighbors. So it's going to be just a hair easier to take away this electron than any of the 3 that were there before. As a result, the group 6 elements, you will see a slight dip in ionization energy, and then the trend picks up again. There are as many ionization energies for an atom as there are electrons. Most of the time when we say ionization energy, we're talking about the first one. That's the energy required to take away the first electron, the first valence one that's available. For the alkali metals, that makes a lot of sense. because there's only one valence. You take away one, and that's the ionization energy, and everyone's happy. But even if you look at the screen here, like magnesium has two valence. It takes a different amount of energy to get the second valence away from magnesium than it does the first. Every electron you remove from an atom makes it harder to take away the next one. Does that make sense? Well, it should, because when you take away the electron, going back to the tug-of-war analogy here, you now have more protons than electrons left behind, and so the nucleus is pulling hard. And all the electrons that are left behind are held more tightly by the remaining protons. So you take away the second one, the third one is going to be enormously hard. On the chart, you see in the blue area regions where it gets significantly harder to take away subsequent electrons. So like for sodium, it takes 496 kilojoules to remove an electron from a sodium atom. That's a pretty small number, pretty easy. We know sodium is pretty easy. But the second one jumps up to 4,560, almost, but not quite, 10 times. Say 9 times as high. How in the world can it be that much harder? Well, the second number, you're having to remove an electron from the inner core. It's a lot closer. According to Coulomb's law, if it's a lot closer, it's a lot harder to take away because the force is higher. If you look at magnesium, the first one, pretty easy. The second one, it's kind of hard getting there. But by the time you get to the third one, the third ionization energy, it is ridiculous. Again, you're now into the inner core trying to take away a third electron. It's not going to happen. And we can see the same thing with aluminum. By the time you get to taking away the fourth electron, you've gone beyond valence and try to remove from the inner core. It becomes enormously difficult to make this happen. These values can also show you or explain to you why the nonmetals tend to be negative ions and not positive. Look at the first metals. Sodium 496, magnesium 738, aluminum 578. Well, those are pretty low numbers. It's fairly easy to take an electron away from the metals with numbers that low. But look at sulfur and chlorine. That number is almost twice as much. So it's much easier for nonmetals to gain one or two than to overcome that energy and have an electron taken away. My final thought on this is that when you're given data like this and you look across and see the numbers increasing like you would expect, it is a clue that when the number jumps up to ridiculous values, that you are seeing a transition from removing from the valence shell to removing from the inner core. So standardized test questions can just give you a chart, and based on the ionization energies here, what is the most likely element shown? And then where it jumps up, how many times it takes to jump up. Let's say if that's 3, it's the I4 that's ridiculously high. That's going to tell you it's a group 3 element. It could be aluminum, it could be boron, it could be gallium, something like that. All right, finally explaining the ionization trend using our 3 very important terms. Why does the ionization energy decrease as you go down a column? Well, as we go down, the element gets bigger, and the valence electron is further away from the nucleus. And we have learned already that the force that the valence electron is being held is inversely proportional to the distance squared. So if the electron gets further away, the force holding it is going to get very low, and we're going to see a decrease in the strength. It'll be easier to remove. Why does the ionization energy increase as you go from left to right across a row? Well, we can also use Coulomb's law to kind of explain this, but instead of distance, we're going to use the Coulomb's law part that says the force is proportional to the charge Q. On any row, all the atoms have valence electrons on the same level. the same energy ring, so the distance is about the same. But we know that the nuclear charge increases. The effective nuclear charge is increasing as you go from left to right. The shielding stays the same, so according to our Coulomb's law, if the Q is going up, that is the effective nuclear charge, the force of attraction will increase. And so it will be harder to remove the electrons as you go to the right-hand side of the periodic table.